Good morning, friends. Today we are starting a new lesson, namely modeling and performance of transmission lines. Myself, Dinesh K, Assistant Professor, Electrical and Electronics Engineering. Before moving to this topic, I'll just reduce the portions covered to be in this session. Otherwise, these are all my lecture objectives for the entire session. First, I have to classify the overhead transmission lines. What are the classifications of overhead transmission lines available, and what are the important terms required for the modeling and performance of transmission lines, and the performance of single phase short transmission lines, three phase short transmission line. And this performance is basically for your single phase, and this performance is for your three phase. Next one is effect of load power factor on regulation and efficiency. Medium transmission lines. In medium transmission lines, we have three classifications: Saint condenser method, nominal T method, nominal pi method, long transmission lines. So in the long transmission lines, we have to analyze the transmission line using your regress method. And next one is generalized circuit constants of the transmission line. What are the generalized constants available for the circuit constants? That is your transmission line circuit constants. And determination of generalized constants for transmission lines. So for the entire case of the transmission lines, that is nominal pi method, nominal T method, end condenser method, and long line method, short line method. The following methods we are going to determine the generalized constants for the transmission lines. So these are all the topics I'm going to cover in this session, and it is said to be an objective of the entire session. And first, I move on to the introduction portion. So in the introduction portion, the important consideration in design and operation of transmission line are the determination of voltage drop, line losses, and efficiency of the transmission. So these are all the three main objectives while we design our transmission lines. So the voltage drop. So we have to minimize our voltage drop as much as possible, and minimize our line losses as much as possible. And the efficiency of transmission, we have to improve this efficiency of transmission as much as possible. And these are all the important considerations of your design and operation of a transmission line. So for these three considerations, that is voltage drop, line losses, and efficiency of transmission, so these three values decides this considerations. That is, these values are greatly influenced by line constants, resistance, inductance, and capacitance of the transmission line. So these values plays a vital role while you designing the design consideration for the transmission line. So what happens if we design the values of R and L and C values properly? Firstly, we have an opportunity to understand the effects of the parameter of the line and burst voltages and flow of power. We are able to determine the burst voltages and flow of power effectively. And secondly, they help in developing an overall understanding what is occurring in electric power systems. That is, the current trend we may analyze with the help of the modeling and performance of the transmission lines. So these are all about your introductions of your modeling and performance of a transmission line. So next one is my classifications. So based on the three constants we have, that is R, L, C, we have to distribute it uniformly along the whole length of the line. So the values of R, L, C is invisible in nature, but the character or the nature of the component is available in the transmission lines. That is, your R, L, C is distributed uniformly along the whole length of the lines. So here my resistance and inductance form the series impedance, I may say as Z. So people famously said to be Z equal to R plus J XL. Your R stands for resistance and XL stands for your reactance. So the combination of resistance and reactance is nothing but your impedance. So the resistance and inductance competence, that is your reactance due to the presence of inductance XL value. And in some cases, the capacitance existing between conductors for single phase line or from a conductor to neutral for a three phase line forms a shunt path throughout the entire length of the line. Yes, in some cases, that is your length of the line is more and more, we have the effect of capacitance in your line also. For the case of single phase, we may have the capacitance effects. In three phase, it forms the capacitance effects form between your line conductor to neutral conductor. So in the parallel branch, we have the effect of capacitance. So your capacitance effects introduce complications in the transmission line calculations. So depending upon the capacitance calculations, we have three types of line classifications are available. And number one is short transmission line, and second one is medium transmission line, and third one is long transmission line. So we are going to discuss the short transmission line analysis and medium transmission line analysis, long transmission analysis in detailed manner. So far we have classifications of transmission, overhead transmission line is three categories. One is your short line transmission, medium line transmission, and long line transmission. We are going to discuss one by one in detail. So yes, first one is my short transmission line. So when the length of an overhead line is up to about 50 km, that is the range of 0 to 50 km is considered to be a short transmission line, and voltage range should be less than 20 kV. So it is usually considered as a short transmission line. So we have to remember in our mind. So the length of the transmission line is within 50 kilometers, and voltage range is less than 20 kV. So this quantities of this consideration is usually said to be a short transmission line. So due to the smaller length, that is your length of the transmission line is only 50 km, within 50 kilometers, and lower voltage, that is less than 20 kV. So the capacitance effects are very small in this kind of transmission line. So we may neglect our capacitance effect. So therefore, while studying the performance of the transmission line, only resistance and inductance of the lines are taken into account. It is only applicable for your short transmission line, not for your medium line as well as long line. So we have to remember the operating voltage for the short transmission line is less than 20 kV, and the distance carried out is less than 50 kilometers. So here we have to neglect our capacitance. So next one is my medium transmission line. So here my length of an overhead transmission line is about 50 to 150 km. So the range of the kilometer distance is given, that is 50 to 150 km, and line voltage in this system is moderately high. So the line voltage obviously 20 kilovolt, that is greater than 20 kilovolt, and less than 100 kV. So this kind of specification is said to be a medium transmission line. So here we have a sufficient length and sufficient voltage. So obviously we have the effect of capacitance also. So we have to take an account of the capacitance for the mathematical calculations or analysis purposes. So here for the purpose of calculation, the distributed capacitance of the line is divided and lumped in the form of condensers. So most of the times the capacitance values are treated as condensers only. So it is available one or more points. This the capacitance of the line is divided and lumped in the form of condensers shunted across the line at one or more points. Yes, next classification is a long transmission line. So here my length of the overhead transmission line is much more. We have more than 150 km. Line voltage is very high. It is also greater than 100 kV. So this kind of consideration is said to be a long transmission line. So for the treatment of such a line, the line constants considered uniformly distributed over the whole length of the line. Rigorous method employed for the solution. So we are not solving our solution in a easier manner or in a Phasor manner, just like your short line or medium line. So we have to perform the rigorous methods. We have some sort of differential equations to solve this kind of long line transmission networks. So we may discuss in the derivation portion for the long line transmission lines. So we have to remember the operating voltage for the long line transmission is more than 100 kV and distance is more than 150 km. I move on to the next slide. Yes. The important terms available in the modeling and performance of the transmission lines. It is one of the much essential terms needed for the entire topic. That is, number one is voltage regulation. So how much of voltage is regulated in the transmission lines is an important consideration. Next one is my transmission efficiency. So these two things are my problem definition. So a design engineer or transmission line engineer how to design the voltage regulation and transmission efficiency properly. Then only a consumer receives his power as easy as possible, as economic as possible. In this manner, they are getting the feasible electrical power using these two terms. That is, the consumer can easily adopt the voltage regulation in an effective way and transmission efficiency in an effective way. These two are very important terms. It is applicable for the industrial customers as well as domestic customers. Yes, first I have to express my percentage regulation. So the difference of voltage at the receiving end of the transmission line between the conditions of no load and full load. So the difference between your no load and full load conditions is said to be an voltage regulation with respect to your sending end voltage. Yes, the sending end voltage to receiving end voltage difference is nothing but your percentage voltage regulation. It is usually expressed in percentage. So only the formula is indicated as percentage regulation equal to Vs minus Vr by Vs into 100. So what is one of the important definition available for the power system modeling and performance. So next definition is my transmission efficiency. The ratio of receiving end power to the sending end power of the transmission line is known as transmission efficiency of the line. So the percentage transmission efficiency in symbol wise it is denoted by eta suffix capital T. So nothing but receiving end power by sending end power into 100. So this is my two important terms available in the power system modeling and performance. So next one is performance of a single phase short transmission line. So here I am having my power circuit. So in this power circuit a simple model is given. So here I am having my series resistance, series reactance XL. Series resistance I am naming as R and series reactance I am naming as XL. So in between your R, XL I may connect my load is also in series. So in the entire length of the line I may connect my R, XL and load in series, and this is my Vs is nothing but sending end voltage. My current I is circulating through the entire line. So in the load terminal, that is across your load terminal, we may get a receiving end voltage. So this particular condition is adopted for your short transmission line. So the effect of capacitance is absent because due to its short length. So the terms used in the circuit is I is my load current, R is my loop resistance, that is resistance of both conductors, and XL is loop reactance, VR is receiving in voltage, cos pi R is receiving in power factor. Usually it is preferred as lagging power factor conditions, and Vs is sending in voltage and cos pi is sending in power factors. So these are all the terms available or relevant to the circuit. Yes, next I am construct my phasor representation for the circuit diagram. Yes, so in this phasor representation, my current I is taken as a reference phasor. What is your current? Here the line O to D is my reference line. So the current line is the horizontal line located here. That is OED line is nothing but your current line. So I am taking this current line as a reference. So next construction is my OA. So the OA line. So OA line represents your receiving end voltage Vs. So this Vs leading your current by an angle phi r. So the supply voltage at the receiving end side is leads by an angle phi r with your current capital I. So this is my second step. So first step, I am taking my current as reference, and second step, my OA is my receiving end voltage. It is leads with your current by your phase angle phi r. So the next step, your AB represents drops IR in the drop in IR. So it is in phase with your current. That is this line. So the line AB is nothing but your receiving end resistance drop. So I into R. So it is your permissible resistance drop in the receiving end side. So this AB is in phase with your reference current I. So next one is my BC. So BC is my inductive voltage drop. I am naming the inductive drop as I times of XL. So this I times of XL leads your current. That is, this current is 180 degree. So this current from the point B, it leads by 90 degree. So next one is my initial considerations are R or O1. First one is my OI is reference, OA is my receiving end voltage, and receiving side drop is AB, that is due to resistance, and receiving end drop in terms of inductance is I times of XL. At last, my motive is I have to find out the sending end voltage OC. So when I am joining the line O and C, I may get my VS line. Otherwise, we may say your VS equal to VR plus IR plus IXL. Otherwise, it is simplified as VR plus I times of Z. So this is the simple Phasor construction adopted for the short transmission line. So next one is the governing equations available with respect to your Phasor diagram. So here I need my OC. OC is nothing but this line. So I need this line OC. So OC square equal to OD square plus CD square or DC square. From this right angle triangle, I am going to calculate what are the numerical values belongs to the circuit. So the OC square equal to, that is my VS square equal to OD square plus DC square. So OC is nothing but your VS squared OD. So the line OD is nothing but OE plus ED. So OE square plus ED square is nothing but OD square. I am written here. Next one is my DC. So DC is nothing but DB plus BC the whole square. So here I am written. That is OE plus ED the whole square plus DB plus BC the whole square. So this is nothing but my VR square. So I am substituting the exact values for the OE, ED, DB and BC. So first I need to determine what is my OE. So the OE line is located here. So in this line we have our receiving end voltage in phase with your current with your cosine of the angle. So only I am substituting VR cos pi r. And ED is nothing but your drop due to the resistor, that is your AB line, it is exactly in phase with your current ED. So here the same value, IR value existing in ED also. So the value is IR the whole square, that is VR cos pi r plus IR the whole square. Next one is my DB. So DB is located in this place. So DB is here the same receiving and supply here with respect to the cosine. Sorry, sine. So DB is with respect to sine and OE is with respect to cosine. So I am substituted here, that is VR sine phi r, and BC is nothing but drop due to the inductive reactance. This one, I times of XL BC. So I am substituted here. So at last I may get my VS, which is equal to square root of VR cos pi r plus IR the whole square plus VR sine phi r IXL the whole square. So the first parameter for the short transmission line is percentage voltage regulation. It is difference of your sending end voltage to receiving end voltage by receiving end voltage into 100. Next one is I may easily determine my sending end power factor cos pi s. So cos pi s is nothing but OD by OC. So OD by OC is nothing but my sending end power factor that I have to determine. Next one is my power delivered. Power delivered here is VR IR cos pi r. Line losses in the entire short transmission line is I square r. power sent out is VR IR cos pi r plus my drop line losses I square not losses. At last my percentage transmission efficiency is power delivered by power sent out into 100. So mathematically I may express power delivered as VR IR cos pi r divided by VR IR cos pi r plus IR square into 100. Using this expression for the short transmission line, you may get your percentage transmission efficiency, power sent out, line losses, power delivered. So these are all the important formulas available to solve your short transmission lines. You may directly take in an account for solving your numerical examples. Yes, the next one is an approximate expression for finding your sending end voltage. This is an approximate expression. An approximate expression for the sending end voltage Vs can be obtained as follows. Here I have to draw a perpendicular line BC here. The same phasor whatever I am having in the previous is I have to draw a perpendicular line BC on OA. So in this line I draw a perpendicular line produced as shown in figure. The OC value is nearly, I am extended my OC line to OF line. So this line I am equating the entire O to C line to O to F line. So when I am extended this kind of considerations, my phasor should be modified. Here my VR is my reference and phi r is lags by phi r degree, and my drop is IR, and reactance drop is I into XL. When I am adding these three values VR, IR, IXL, I may get PS. Here my current is lagging. So from this I am getting my OC is nothing but OF. That is OF is nothing but OA plus AF. OA plus AF. AF is nothing but AG plus GF. So further I am going to simplify as OA AG as it is GF is also equal to the extension of the line BH. So this value and this value is almost equal. So I am equating GF equal to BH. So the sending end voltage for the phasor diagram is VR IR cos pi r and IXL sin phi r. So next one is my solution in the complex notation. So what is the need for the complex notation is it is often convenient and profitable to make the line calculation in the complex notation. So here I have to chosen my VR as my reference phasor, that is this phasor diagram. Here I have to choose for the complex analysis this phasor diagram. My VR is my reference phasor, and in order to your phasor diagram, the Vs is nothing but the phasor sum of your VR vector and the I set. So this Vs is nothing but phasor sum of VR vector and I set. So this drop due to resistance and reactance. So VR is assumed as VR plus J0 in terms of complex quantity, and I vector, the current flowing through the entire circuit is marked I vector at an angle minus phi r. Because why I am using the minus sign means because your current is lagging here. So the current lags your VR with an angle phasor phi r. So only I am indicating here a negative sign, that is angle of phi r. So the phi r is modified as I times of cos phi r minus J sin phi r. And your Z is nothing but R plus J XL. V is equal to VR I into Z. So I know the value for VR vector, VR plus J0, and I value, I is nothing but I cos phi r minus J sin phi r. That is nothing but R plus J XL. So when I am simplifying these values, I may get VR plus IR cos pi r plus I XL sin phi r plus J I XL cos pi r minus IR sin phi r. This is my sending end voltage. That is my Vs. In terms of Vs is whole square root of VR plus IR cos pi r IXL sin phi r the whole square plus IXL cos phi r minus IR sin phi r the whole square. The second term under the root is quite small, that is this term IXL cos phi r IR sin phi r is quite small and can be neglected with a reasonable accuracy. Therefore an approximate expression for the Vs becomes Vs equal to VR plus IR cos phi r IXL sin phi r. So this expression is approximately similar as we find out in the earlier case, that is your actual calculations. So complex calculation as well as your regular calculations receives the same answers for Vs. Yes, two important note how to be taken for this relation. Now the approximate formula V is equal to VR IR cos pi r plus IXL sin pi r gives fairly correct results for the lagging power factors. However, in some cases you may get appreciable error is caused by leading power factors. Therefore, approximate expression for Vs should be used for lagging power factor. So short transmission line prefers always a lagging power factor conditions only. So in this method, your solution is most complex, available in the complex notation, and is in the more presentable form. Yes, next one is my three-phase lines. So the three-phase transmission lines, I am connected my three-wire. So in terms of sending end and receiving ends, I am forming a star for the sending end supply. So three coils, I am having three loads, I am having. In between we have the transmission line constants RHXL, RXL and RXL. So I'll just approximate the three phases into a lumped form. So whatever we have in this star connection is in the distributed form. So I have to conveniently modify this circuit in the lumped form. That is I times R XL and connected by load in between your line and neutral. So we may get our phase values. So my sending end side and the receiving end side, my circuit becomes more and more simple here. So the effect of load power factor on regulation and efficiency. So regulation is changed now. For the case of single phase line, the voltage regulation is Vs minus Vr by Vs into 100. But in the case of three phase line, the voltage regulation is purely applicable for your lagging power factor as well as leading power factor. So here the percentage regulation for the lagging power factors IR cos pi r plus IXL sin pi r by VR into 100 for lagging power factor conditions. Next one is the percentage voltage regulation, which is equal to IR cos pi r minus IXL sin pi r by Vs into 100 for leading power factor conditions. So this kind of effect takes place for your three phase lines. So based on that two expressions, we have four conclusions. So when the load power factor is lagging or unity or such, leading that IR cos pi r is greater than IXL sin pi r, then voltage regulation is positive. That is, receiving end voltage VR will be less than the sending end voltage. Yes, in most of the cases, these things would be happening. And the receiving end side, we are not getting the actual voltage as we are sending in the sending end side. So the voltage is dropped due to this reason only. So the power factor is lagging or unity or such, leading the IR cos pi r is greater than IXL sin pi r, then voltage regulation is positive. Then the receiving end VR will be less than the sending end voltage. Yes. Next one is for the given receiving voltage and current, the voltage regulation of the line increases with the decreases of the power factor for lagging loads. And third conclusion obtained from the expression is when the load power factor is leading to this extent, that is IXL sin pi r is greater than IR cos pi r. Then voltage regulation is negative, the receiving end voltage VR is more than the sending end voltage Vs. So it is your extreme cases. So this effect is also said to be a Ferranti effect. Next, the fourth conclusion is for a given VR and I, that is your receiving end voltage and current, the voltage regulation of the line decreases the decrease in power factor for leading loads. Next one is effect on transmission efficiency. So the transmission efficiency effect for the three-phase transmission line is P, which is equal to VRI cos pi r for single phase line. So from this expression, I may get my current. Current is nothing but P divided by VR cos pi r. Similarly, for power for a three-phase line, that is P equal to 3 times of VRI cos pi r. Similarly, current I, which is equal to P by 3 into VR cos pi r. So these are all the effect caused due to the three-phase transmission line. So exactly similar, the rest of the values, that is Vs vector, Vr vector, I vector, all the values are same except the power and the current expression and your regulation. So regulation is applicable for your leading case as well as lagging case. We may continue in the next session. Thank you.